Good morning and welcome to Tech 259 on Monday, April 12th. Today we're going to talk about different classes or designs of generators, but first let's review the problem set from last time. So this was problem set number 16 about generator frequency and voltage control. So I'm going to switch over to my document camera. All right, the first three problems in problem set number 16 were about frequency control. And the next three problems were about voltage control. So number one says that we have a no load operating frequency set point of 61.0 hertz. So that's this point right there. And a full load operating frequency of 59.0 hertz. So that's this point right here. This is called a house curve, you'll recall from last time, because it kind of looks like the roof of a house, kind of, if you draw some lines down here especially. And on the horizontal axis, we have the real power output of the generator in megawatts. And what we're trying to find out in question number one is what is the frequency droop, which you can think of as kind of the slope here. It's kind of like the slope of this line. It's not calculated exactly like the slope of the line, but it's the same kind of general principle. And we have an equation for frequency droop. It is no load frequency minus full load frequency, that minus that, divided by the full load frequency times 100% to get it into a percentage. So we have all that information. So number one is pretty straightforward. We plug in our no load frequency of 61 hertz, our full load frequency of 59.0 hertz, and we divide by our full load frequency of 59.0 hertz, multiply it times 100%, and we get a frequency droop of 3.4% for number one. So that's good for number one. Then number two, it says we have the same set points as we had in number one. So we have a no load frequency of 61 hertz, a full load frequency of 59.0 hertz, and it says the rated power capacity is 100 megawatts. So that means at full load power, that's right here, we have a power output of 100 megawatts. And right now, the grid system frequency is actually 60.1 hertz. So we're operating right here. Here's our operating point on the house curve. And here is our operating system frequency right now. So the question is, what is this point right here? Because we know that this is a straight line. The generator is operating somewhere on this straight line. We're given a bunch of the parameters of this line, like the no load frequency, the full load frequency, the full load power. So we can use all that information to find out what is this value right here for the actual operating power output right now. Fortunately, we have an equation for that. And that is equal to the actual power output right now is equal to the full load power times this ratio. Think of this right here, this divided by this as a ratio. It's the no load frequency minus the system frequency divided by the no load frequency minus the full load frequency. So think about how that pertains to this graph right here. This ratio is no load minus system frequency. That's from here to here, as a ratio of this full range, no load minus full load, here to here. So what we're really doing here, this is really just kind of a ratio. We're taking, okay, what's the maximum power this generator could produce? That's this. And the rest of this is just a ratio. We're saying, okay, how far down on this curve have we gone? How far down here from no load to full load are we traversing down this curve? So it's just the no load minus system, that's this part, as a ratio of this full range right here, from here to here. All right, hopefully you can see that really this is just a ratio. We're taking that times the maximum power it could produce. All right, so qualitatively, I think it's helpful to understand what we're doing and why we're doing that. So we can plug in values here. Here's our full load power. There's our no load frequency. There's our actual operating system frequency right now. And we take that divided by the full range from no load to full load, 61.0 hertz minus 59.0 hertz. And we come up with an answer of 45 megawatts. Because all these hertz, they cancel out. You subtract this minus this, you get hertz. Subtract this minus this, you get hertz. So those hertz cancel out, and you're left with megawatts as your unit. So 45 megawatts is the answer for number 2. Number 3 is a bit more challenging. So I would say number 3 is probably the most difficult question in this problem set. It's not, you have to use a little bit of critical thinking to solve this. So I will say also, before I talk through this, there's more than one way to do this. So I will talk through the way that I thought was most intuitive to me. But I'll also mention there's a different way to do this as well that maybe was more intuitive to you. So here's what we're trying to do. What are we trying to do here? We have an AC generator, and it has a rated power capacity of 500 megawatts. So that's this right here. We have 500 megawatts. That's the maximum power output. And we know it has a 2% frequency droop. All right, so back up here, we calculated the droop. Now this generator in number 3 has a 2% frequency droop, not a 3.4%. So you got to discard what you did in number 1 and number 2. But we can use those equations still with a 2% frequency droop. Right now, its real power output is 300 megawatts, and the grid system frequency is 60.0 hertz. So we know where it's operating at on this curve. We know right now its system frequency and its real power output right now. What is the generator's no load frequency set point? All right, so we have, what do we have right here? We have the droop, through which maybe we could find the no load or the full load frequency set point. And we have where it's operating at right now. We have the operating system frequency and we have the operating power output. But that's it. We don't have the no load frequency or the full load frequency. So that is a bit of a problem for us right now, because look at our equations. Here is one equation that we've used so far, and it has the no load frequency here and here, as well as the full load frequency right here. So we're not going to be able to directly use this equation for anything because we don't know the no load or the full load frequency in number 3. So we can't directly use this equation. If we look at our droop equation, we have this equation for the droop. We know it's equal to 2% in number 3, so maybe we can use that. But look at this equation too. It uses the no load frequency and the full load frequency. So I can't directly use that either. So what I'm going to have to do here is I'm actually going to have to use both of these equations, the droop equation as well as the power equation. And what I'm going to have to do is solve for the no load frequency in terms of the full load frequency, or vice versa. I could solve for the full load frequency in terms of the no load frequency. Basically, what you end up here with what you would end up with here, you have two equations that each have two unknowns. That's the issue. You know, it's kind of like what you've got here is basically like x plus y equals 5, x minus y equals 1. That's really what you've got here. The equations are slightly more complicated than that, but that's the essence of what you got here. So you got two equations that are relevant to this plot right here. This plot right here. You've got your power equation that we used in number 2, and you got your frequency droop equation that we used in number 1. Both of those equations have two unknowns, that we don't know in problem number 3. And those unknowns are the no load frequency and the full load frequency. So what you're going to have to do is you're going to have to pick one of those equations and then solve for the no load frequency in terms of the full load frequency. So you'll end up with something like no load frequency equals 1.05 times the full load frequency, or something like that. Or you could do the opposite. You could solve for the full load frequency in terms of the no load frequency, if that's the opposite of what I just said. But basically you'll solve for one in terms of the other, and then plug that into the other equation so that you can get one equation with one unknown, so you can solve for that. So that's the essence of what we're going to do here. All right, so I chose to start with the Droop equation, but you would not have to. But that's what I did. So I said, I'm going to use a frequency Droop equation like we used in number 1. And I'm going to write that down, the no load frequency minus the full load frequency divided by the full load frequency times 100%. That's from the Droop equation, equals 2%, because we know the frequency droop is 2% in this equation. So I'm going to divide both sides by 100%, and I'm going to multiply both sides times the full load frequency. When I take 2% divided by 100%, I get 0.02. And I'm going to multiply both sides times the full load frequency, like I said. So on the right side, I get 0.02 times the full load frequency. And on the left side, I just get this numerator right here. So I have the no load frequency minus the full load frequency equals 0.02 times the full load frequency. And now I'm going to solve for the no load frequency in terms of the full load frequency. So that's pretty easy to do here. What I'm going to do is I am going to, well, I've got a negative sign here. So what I'm going to do is add the full load frequency to both sides. And then I get the no load frequency equals the full load frequency plus 0.02 times the full load frequency. So you could simplify that even more and say no load frequency equals 1.02 times the full load frequency. You could have that right here, but I didn't. I just left it like this. All right, so good. Now we've got the no load frequency in terms of the full load frequency. So now I can use my other equation and I can solve for the full load frequency. I can plug this in to the other equation so that I get one equation with one unknown. All right. So what you could do here, this is another option. Like I said, there are different ways to solve this problem. What I could do is I could plug these, this expression into the power equation, which I have not used yet. And you could solve for the full load frequency, and you could find the full load frequency with that. And then you could solve based on the Droop equation. You could go back and solve for the no load equation, no load frequency. I did it just a little bit differently here. I did it a little bit more based on kind of intuition, all right, or kind of graphically, all right, because look at what you've got right here. So this is what we know so far. Here's our operating curve, our house curve, and we're operating right here at 60.0 hertz, and we know that the real power output is 300 megawatts. And we also know that the rated power output, the full power output, is 500 megawatts. But we don't know this no load frequency, and we don't know this full power frequency, right? But we do know that our power output is 3/5 of the way toward full power output. You know, on the range of 0 power to max power, we're 3/5 of the way along that curve. So if we're 3/5 the way along the curve in this direction, we must be 3/5 of the way along the curve in this direction as we're going from no load frequency to full load frequency. All right, hopefully that makes sense. If we're 3/5 of the max power output, then we're 3/5 of the way along the curve in this direction horizontally. And if we're 3/5 along the curve in the horizontal direction, we must also be 3/5 of the way along the curve from no load frequency to full load frequency. So this point must be 3/5 of the way from here to here. All right, that's what I mean by the graphical intuition that I'm going to use here to actually solve the problem. All right, so that's what I'm doing. What I'm doing here is I'm going to say that the system frequency, 60 hertz, is equal to this full load frequency plus 2/5, because that's what's left over, right? We're 3/5 from here to here. So from here to here is 3/5 of the way. And from here to here is 2/5 of the way, all right, along the curve from no load to full load frequency. So what I'm doing is I'm saying the system frequency, 60 hertz, it's equal to the full load frequency plus this amount right here, this amount right here. And this amount right here is 2/5 of the way from here to here. So that's what this says. 60 hertz is equal to the full load frequency plus 2/5 of the way from the no load frequency minus the full load frequency. All right, so hopefully you understand where this equation comes from. Okay, so now I'm going to substitute for the no load frequency because I can't solve this equation. It's one equation with two unknowns, no load frequency and full load frequency. But if I substitute for the no load frequency, I can get rid of one of those variables and I can get one equation with one unknown and I can solve it. So I'm going to substitute for the no load frequency. So I'm going to plug this in where I see full load frequency. So I have 60 hertz is equal to the full load frequency plus 2/5 times the quantity. Now I plug in. So this comes from this right here. Full load frequency plus 0.02 full load frequency minus full load frequency from right here. Now you can see in this equation, I only have one variable, full load frequency. So now I can cancel these because I'm adding full load frequency, then I'm subtracting full load frequency. So these just cancel out. That's nice. And so I get 60 hertz equals the full load frequency plus 2/5 times 0.02 times the full load frequency. So that works out to 0.008 times the full load frequency, which means that 60 hertz is equal to 1.008 times the full load frequency, which means solving for the full load frequency, that's equal to 59.5 hertz. Okay, so now I know the full load frequency, but what I wanted to find was actually the no load frequency. All right, so maybe I should have done this a slightly different way. Maybe what I should have done in hindsight was I should have done the opposite here. I should have solved for the full load frequency in terms of the no load frequency, and then plugged in here for the full load frequency here and here, because then I would have solved directly here for the no load frequency, and that would have made it, we would have been done by now. But I didn't, and that's okay. Sometimes I like to demonstrate a long way of doing things, just to show that you can do it in multiple ways. So, all right, we've got the full load frequency here, but we're trying to find the no load frequency, but that's no problem because now I can use any of these equations because now I know what the full load frequency is. That's a known, so it's not an unknown anymore. So now I'm going to use the Droop equation, and now I can plug in for the full load frequency and the Droop, and the only variable will be the no load frequency. So that's what I did down here. Here's the Droop equation. I know the frequency Droop is 2.0%. So I plug in for the full load. Actually, what I did here is I divide both sides by 100% and then multiply both sides times the full load frequency. So I get the no load minus the full load equals 0.02 times the full load frequency because I multiplied that times both sides. And now I can plug in for the, now actually what I did here, I added the full load frequency to both sides. So now I get the no load frequency equals 1.02 times the full load frequency. And now I can plug in for the full load frequency. That's this right here. So pull that down, plug it in. 1.02 times the full load frequency is 60.7 hertz. 60.7 hertz, that is the no load frequency set point of our operating curve right there. That was the toughest question in this problem set. So if you get that one, then the others should be pretty straightforward. So let's go on to number 4. The next 3 are going to deal with voltage droop instead of frequency droop. And remember, while frequency is connected to real power output, the voltage is connected to the reactive power output. All right, so in number 4, we say we have a generator that has a no load voltage set point of 610 volts and a full load voltage of 595 volts. So once again, we have our house curve. We just have different units on the axes. And our no load voltage is 610 volts. You probably can't read that, but it says 610 volts. And the full load voltage is 595 voltage. We want to find out what is the voltage droop of the machine. So this equation is our voltage droop. It looks very, very similar, almost identical to the equation for frequency droop, but we have voltage values instead of frequency values now. So we just plug in our value for no load voltage and our value for full load voltage from the givens here in the problem, and take it divided by the full load voltage times 100%, and you get 2.5%. For number 5, we are told that we have a generator with a rated, that's maximum reactive power capacity of 300 megavar, and it's operating with the same set points as in problem number 4. And the current system voltage, that's the operating point, is 600 volts. What is the machine's reactive power output at the current time? Okay, so it has the same operating set points as number 4. And right now, our system voltage is at 600 volts. That's the output. So given these operating parameters and the droop and everything, we want to find out how much power, how much reactive power is it producing right now? So that's a question mark right there. What's its reactive power output right now? Fortunately, we have an equation for that we can plug directly into. So we have our reactive power output is equal to our maximum reactive power output times, once again, this ratio. I want you to see that this is really just a ratio. This is the no load voltage minus the system voltage. That's this minus this. And then we're dividing by the no load minus the full load voltage from here to here. So this right here is really just a ratio of how much has it dropped or drooped from here to here compared to the maximum that it could droop from here to here. All right, so that's really just a ratio. Okay, so we plug in values. There's our no load voltage. There's our actual operating system voltage. And here's our no load voltage minus our full load voltage. Plug in there and your volts units will cancel out and you're left with megavar. So our answer is 200 megavar, volt amps reactive. Okay, then number 6. Number 6 is a little bit like number 3, but it's not quite as bad. It's not quite as difficult as number 3. So in number 6, we have an AC generator with a 2% voltage droop. It's currently operating at a system voltage of 4.5 kilovolts. And it's producing 5.0 kilovar of reactive power right now. If the full load voltage of the machine is 4.45, so that's this right here, what is the maximum reactive power output of the machine? Well, I do have an equation that has the maximum reactive power output in it. It's this one right here that we just used in number 5. Q sub FL. That is the maximum reactive power output of the machine. So I'd like to use this equation right here in number 6, but there is a problem because when I look at this equation, I take I can solve for this, right? I can rearrange the equation and solve for this, but I'm going to need to know not just the system voltage, which we do know in number 6, and not just the full load voltage, which we do know in number 6, but I also need the no load voltage, and I don't know that in number 6. So right now, I can't use this equation in number 6 yet, because this is one equation with 2 unknowns. This is one unknown, and this is one unknown. No load voltage is an unknown. So I can't use that yet, but I do have another equation that is relevant to this situation, and that's the voltage droop equation. So take a look at this voltage droop equation that we used in number 4. I do know the droop because it tells me in number 6 it's 2%. And I do know the full load voltage. So the only unknown in the droop equation is the no load voltage. So I can solve for the no load voltage with the droop equation. And then once I know the no load voltage, I can plug that into the reactive power equation here and here, and I can solve for the full load reactive power, which is the maximum reactive power of the machine. So that's what I'm going to do. This is the equation that I want to use, but I can't yet because I don't know the no load voltage. So I got to use the droop equation first. And I set my droop equation equal to 2%. So no load voltage minus full load voltage divided by full load voltage times 100% equals 2%. That's from right here that was given. And then I'm going to divide both sides by 100% and then multiply both sides times the full load voltage. So I get no load voltage minus full load voltage equals 0.02 times the full load voltage. And then I'm going to solve for the no load voltage. So I take the full load voltage and add it to both sides. So I get the no load voltage equals the full load voltage plus 0.02 times the full load voltage, which means that now I can plug in values because I know the full load voltage. I know that and that. So the no load voltage equals 4.45 kilovolts because that is the full load voltage. So the no load voltage equals from here 4.45 kilovolts plus 0.02 times 4.45 kilovolts, because once again, that's the full load voltage. Okay, so I solve that and I get the no load voltage, that's this point right there, is equal to 4.54 kilovolts. Now I know the no load voltage and the full load voltage and the system voltage, so now I can plug that into the power equation, the reactive power equation. So I have this equation, but I want to know what is the full load power. So what I did here, I went ahead and plugged in values. So my actual reactive power output right now is 5.0 kilovar. So plug that in. And then our no load voltage, we just solved for, it's 4.54 kilovolts. System voltage is given, it is 4.5 from right here, 4.5 kilovolts. And our no load voltage, once again, is 4.54 kilovolts minus our full load voltage. And we're told that is 4.45 kilovolts. So now what I can do, I can solve for the full load voltage by multiplying this times both sides of the equation and dividing by this on both sides of the equation. So that's what I do down here. I'm rearranging this equation down here. And when I solve that, I get a full load reactive power output of 11.25 kilovar. 11.25 kilovar or 11.25 thousand volt amps reactive, or 11,250 var or volt amps reactive. Okay, then the last problem, number 7, is just more of a qualitative question. This really reminds me of what happened about 2 months ago now in Texas. This is exactly what was happening in Texas. So you could just kind of replace this Eastern interconnect with the Texas grid called ERCOT, Electric Reliability Council of Texas. It's the Texas grid. And what happens if a 1,000 megawatt generator were to suddenly trip offline on a grid? What would happen to grid frequency and voltage? Show the reason for these effects by using house diagrams. So I'm not really asking for any calculation here. I just want to see that you know how to use house diagrams and what happens as something changes in the operating parameters. So the first one I drew here is frequency in hertz versus power. And here is an example operating curve. And initially before a 1,000 megawatt generator, before it drops offline, we're at some operating point right here, point 1 right here. Then what happens is when that 1000 megawatt generator trips offline, every other generator on the electric grid has to produce a little bit more power to make up for that one that tripped offline. So we're asking it to produce a little bit more power. So we're going from P1, power 1, to P2, power 2. And we follow along from P1 to P2 on the operating curve, and we can see that frequency 2 is below frequency 1, the initial operating frequency. So what's going to happen to frequency when a 1000 megawatt generator trips offline? Well, you can see the operating curve is going to shift from point 1 to point 2. Therefore, the frequency of the electric grid is going to decrease by a certain amount, depending on the droop and depending on the, what's left on the electric grid. But it's definitely going to decrease by a certain amount. All right. Similarly, on the voltage house curve, I've got voltage on the vertical axis, reactive power on the horizontal axis. So once again, before it trips offline, I'm here at point 1 with a certain operating voltage and a certain reactive power output. Then when the generator trips offline, then every other generator on the electric grid has to pick up and provide a little bit more reactive power. And so we're shifting from here to here, Q1 to Q2 on the curve. And when I shift from point 1 to point 2 on the curve, you can see that the new voltage, V2, is less than the initial voltage, V1. As I shift from point 1 to point 2, I shift from voltage 1 to a lower operating voltage, V2. So in summary, basically every other operating generator on the grid is going to have to supply a little bit more real power and a little bit more reactive power. And as a result, the frequency and the voltage will both decrease as a result. All right, so that was problem set number 16. That was probably a little bit more challenging, I think, of a problem set than the last couple, but it's really good. It's really illustrative of the way generators and electric grids operate in the real world. So I'm going to end this video now. And in the next video, we'll talk more about different types or classes of generators. So I'll see you in the next video.